Welcome to today's webinar. I'm Erin, one of your resident webinar hosts here at Softree. Today we're going to be talking about surveys, surfaces, and terrain modeling, essentially the foundation of pretty much any project that you're going to do in our software. So today's webinar is not going to be a workflow webinar like we often do. So if you are on YouTube watching this in the future, we are going to drop some hyperlinks into the description of the video. Certainly jump to the data type that is most relevant to you. But yeah, we're going to be going through a whole bunch of different data formats, talking about how to generate surfaces from them, and then talk about some best practices to really help you optimize that model's performance. So quick housekeeping for those of you in the live version of the webinar, thanks for being here. You guys are all muted, so feel free to ask any questions. You just have to type them into that question section. We don't do any out loud questions during the seminar. And then lastly, welcome Matt, resident webinar host here at presenter at Softree. He's going to be tackling all of the fun in-software demonstrations today, and there's going to be a lot of them. So as I mentioned, creating a terrain model is an essential step for every Softree project. We use it as the foundation for road design. We use it as the foundation for site design projects. And really, yeah, it's super important. So today's content, which we're going to cover right now, really important as a foundation for anything you do in our software. So we're going to go through a bunch of, I'm going to say, sections. The first section we're going to tackle is really, the basics. Surveys and topo data that imports as perfectly as it can and creates a surface. We'll go through a couple examples of that just to lay the foundation. From there, we're going to go in and talk a little bit about how we can control that terrain surface or that tin surface, look at contour generation, how you can leverage a 3D view, as well as different feature properties that are going to control how that surface looks and how the different parts of it behave. From there, probably one of our hottest topics when it comes to the support team is big data. So those LiDAR and DEM data sets that we're going to kind of introduce in section 1, they're not always perfect and little and compact and exactly what we need. Sometimes the data sets are monstrous. And in our third section, we're going to look at some different tools and workflows that you can use to control that data set size. Especially when working with LiDAR, DEM, and then contour data that can also end up being a big data set. From there, heading back into conventional data, talk a little bit about import specifications, breaklines, and working with total station or RTK GPS data. And then we're going to wrap up talking about those other formats. Now, these are the ones not quite as common as the conventional data, the DEM or the LiDAR, but here we've got XYZ, which can represent a whole bunch of different data types, DWG, DXF, and then LandXML. And then, not an example, but we're just going to touch on this one because it's so important. It's just the concept of quality and resolution. Okay, action-packed webinar. I'm going to say we're going to go over time. We go over time on non-action-packed webinars, so apologies for the extra 5-10 minutes that we run here today, guys. So section 1, the basics. We're going to take some survey data, turn it into a surface. And this is what terrain looks like before you have data. You open up terrain module and it's going to give you that blank white screen. It needs your data in order to do anything. So in this first section, we're just going to show you that, how to grab some data, 2 formats, LiDAR as well as total station, how to import it, how to create that quick terrain surface. And with that, our first transition of the webinar, Matt, I am going to make you the presenter.
Perfect. Well, we'll start out here and we'll open up terrain. We'll click Insert File. And we're going to bring in our LiDAR data here to start. We'll click Terrain Modeling. We'll create that tin surface. And voila. So pretty simple. That's the LiDAR data. Now, similarly, we could have done that same process with conventional survey data. So here I'm going to bring in, I believe it's a CSV. Yep. Select my IOP. Click Train Modeling, click Generate. We'll skip this. We'll talk about what that is later on. And voila, we've got a surface from conventional survey data for the same area. So at its core, what we cover today is really just expanding on this, going kind of in different directions to talk about some of the nuances. And I'll pass it back to Erin.
Sorry, guys. They added some extra clicks for sharing screens here, and it just keeps throwing us off. Okay, section 2. So now that we've gone through the fastest, quickest, most basic example of survey data import, let's actually start to talk about and unpack what's happening when we create that tin surface, as well as then we'll get into all those nuances with big data, conventional data, and the other formats. So when it comes to your terrain model, what the software is doing is it's taking all of your known data points and it's connecting them with something called a triangular irregular network. And the distance between your points is really going to be, controlling the quality of the surface you're creating. And of course, we'll have a nice slide that gives us a good example of this. But for SRTM data, you might be 50 meters apart in your points, and some UAV data is like 10 centimeters apart. And that quality difference is going to control how many triangles are going to create it, how big your file is, and of course, how accurate your volumes are going to be based on the data that you've got. So here's an example of some medium quality LiDAR data, the triangles created between the points. And we don't look at our software through this. It'd be really, really difficult to design on top of a pile of triangles. So we typically look at it where the triangles are shaded and when they're actually not seeing the outlines of them. And this is kind of the underpinnings of what's happening in terrain. Now, when you import your data, we are typically working with the ground data. Most surveys are coming in, we're getting their DTM. Sometimes we see examples like what you're seeing here in the 3D view. So this is a surface created leveraging the DSMs, the digital surface model, and it's got tree data included in it. And of course, if you start to see spikes like this showing in your 3D view, that is something you absolutely want to address. If your data is classified, you can actually go back to the import and ask for it to say, for example, just be the ground points. And if it's not classified, you're going to want to have a chat with somebody who works with your data or look at a different data format. But yes, just a kind of an asterisk here, just to be aware of what you're importing and what it looks like. And that 3D view that we're going to show you and use today is really important. It can also help you detect for total station data where you've got bad points. So looking at that 3D view, looking at your data, really important. When we go and generate our tin model, much like Matt just showed us, we can include the creation of contours. So we can set whether we want contours for our major and minor, their intervals, and where they occur. And it's important to know that when you add contours to a surface, when you're creating that tin model, those contours are exclusively a visual aid. If you add super dense contours through tin generation, you're not changing your surface. You're just adding a whole bunch of dense additional points to your model, which depending on the model size can make it a lot slower. So really important when you add contours, make sure you're adding the contours that you need from an engineering and design standpoint that you want to have for visuals. Otherwise, yeah, maybe don't even add contours. So a choice for you, again, just a visual aid. And I forgot to mention a big asterisk there. We are actually going to talk about, maybe I'll flip my side back. Sometimes you will actually see survey data that gets imported as contours. And that's really different from contours that we generate from a tin model. So when you import contours as your survey data, totally different. Those are not just a visual aid, that's actually your surface. So yeah, big asterisk, there is that one type of contour format. But for the most part, when you generate your tin, be aware that your contours are just a visual aid. Okay. A couple other points, and I'm going to pass it back to Matt. We have a point ceiling, and I'm sure some of you have hit this before. So our official Softree recommended maximum for modeled points is about 10 million. Of course, this changes a little bit based on your computer specs. So I just wanted to kind of maybe highlight some more realistic maximums, as I know some of you guys run pretty nice computers. So if you're working with 8 gigabytes of RAM, keep to that 10 million model points. If you start getting up into, say 1632, you can start to push past that. Matt today is working with a pretty standard business grade laptop, 16 gigabytes of RAM. He can work with about 16 million model points thereabouts. And as you get to higher performing machines, that is going to keep increasing. But again, official recommended maximum about 10 million, but you can push it based on your specs. And a big reason that we have these limitations to how many points you model really comes down to what the terrain model is doing. And I thought it might be kind of fun to highlight that versus, say, GIS software. So when you import your data into terrain, all of the features, points, data, and information is actually being contained directly in the project file. All of the information is also editable. You can add, delete, change, modify those feature properties anytime to constantly adjust your model. Whereas if you were working in a GIS software, for example, here they're dealing with external references, as well as surfaces being predominantly read-only once they're imported. So really big difference in terms of how you can work with and control that survey data that you've imported. And of course, if you're working in terrain, this is really for engineering type projects, roads, sites, grading, earthworks. That's what we're built for. Whereas GIS, tends to end up in that mapping and more geospatial analysis side of things. So again, because we're being native with our data, because we're included in the format, and because it's not static, there is a point maximum because you're going to need to be able to work with that in real time without any lags. Okay, my last concept, and then more, Matt, is this idea of feature properties. So I mentioned it briefly there. You can change features and modify them, and some of the things you can modify are feature properties. These control whether your points are displayed, or they're connected, or perhaps they have elevation, or maybe they don't have elevation. And if you turn off elevation, that is going to drape a feature on the model. And other examples, if you want it to be included in the tin surface, or maybe it's just a point that exists, it's not part of that, as well as Breaklines. So all of these features can be controlled. We've got a couple great webinars that actually spend a lot of time talking about the different feature properties, and we can certainly link to one of those when we send out the follow-up note. Okay, Matt, I'm going to pass it back to you.
All right. So yeah, I'll kind of expand on what Aaron introduced and kind of show how that behaves in the software and how we interact with things in the software. And continuing off from that example that we've just brought in, well, we can see the LiDAR data that I've brought in here. And if we kind of zoom in, well, we can see that this surface is in fact made up of a series of triangles. We've got our tin, we've created the tin, away we go. Now, with that, when we brought this in, and as Aaron said, we're usually interested in the kind of the DTM side of things rather than bringing in every point, and with LiDAR data, every point that was hit with the scanner. So we aren't interested in the trees and what have you. So if we go back a step to where I grabbed that last data, we can see that I'm using the ground points. So I'm not bringing in every one of those scanner points, I'm using the classified points. Now, I'll just tile my two views here side by side. In my plan view right now, I can't see the individual points that are used to define my model. But when I brought it in, everything would have been selected and we would have had that big magenta blob appearing. So all those points, and in this case, I've got 2.6 million points. They're still in my model, but usually with LiDAR data, we don't want to see it. So each one of these points is not very interesting. It takes a while to draw. So those points, the display property by default is turned off. So we still use them to define the surface. And just to kind of introduce that concept of properties, if we click that LiDAR data, we can see I've got my LiDAR points selected, the ones that are appearing in magenta here. And all the display properties turned off in the properties panel on the right. And then, well, display properties turned off for both plan and profile. I have one feature selected of the 1200 or so in my file. But even though I have one feature selected, I still have 2000 points. So the other concept with LiDAR data is most of the time when we bring it in, we want to have it, I guess, displayed as though it's points. But we kind of group those together for the sake of computing efficiency. Now, those points that we're kind of considering as points, it would look kind of funny if we had them connected. So connected is allowing us to take multiple points, but not show a line connecting the dots. Now, that's kind of an introduction to terrain modeling through the lens of LiDAR data. It's going to be easier to explain things if we focus on the conventional data and how this interacts with our model here. So this one, we've brought it in. We, instead of having 2.6 million points in this file, we only have 4,333. So this model is not really defined by the point density itself. Instead, its quality is really dependent on where the surveyor collected those points and where the surveyor connected those line features. Now, with this, those line features are kind of an important and interesting concept. So here, if we look at, say, this edge of road, this feature, it's being displayed. We can see it in the different views. It's a line feature and it's connected. So from point to point to point, we have a line connecting those, but it's modeled as a break line. So with this being a break line, the triangle edges that define our surface are not allowed to pass through that feature. Each triangle edge there has to follow the edge of the feature itself. And if I were to turn this off, so that break line feature off, and remodel this, we could see, well, what happens when we do that? Suddenly, we can have triangle edges that go through that feature. Again, it's kind of nice to see things in both views here. So if we come down here, I'm going to just show my triangle outlines in my plan view. So I can see I've got a triangle edge that runs from here all the way through to there, whereas if that was a break line, no triangle edge crossing that feature. Now, that's kind of a nice little introduction to the model. Similar to break lines, not every feature is necessarily included in our surface. So let's say, and I'm just going to draw a feature here for the sake of it. Let's put a point there, and then let's make it a little higher. I'm going to make it a little kind of obnoxious in its height. So this point right now, I have the property turned on where it's modeled. So if I click right, I can see that that's included in the tin surface, but if modeled was turned off, that could still be a 3D point, just not connected to the surface. So it's, yeah, these properties ultimately control how our features are displayed and interact with the surface. And then similar to that, we have, well, in line with displaying, if I want to change the line type or color, we can do that with the drop-downs below the properties themselves. Now, aside from just controlling how that surface is created and what we see from the data that we've brought in, of course, we want to evaluate it. And when I brought that in, I very quickly just went over here to the 3D view so I could see the 3D surface of what I'm working with. So that little 3D icon here pops open our 3D view. If it wasn't already open, we could Click that. Generates fairly quickly. There'll be a little bit more of a lag just when we first initialize something with LiDAR data. But of course, that is super valuable in terms of understanding what's going on. Now, aside from just the 3D view, if we were to look at this in our surface, well, maybe we want contours here. So oftentimes when we create our tin surface, and we have a tin surface right now, we don't need to recreate it. But if we wanted contours, we could say I want contours and I want them to be spaced in 25 and 5 meter intervals. And there we are. So that carries forward regardless of whether our data set is LiDAR data or conventional survey data. And here where the LiDAR data is not, each individual point is not that interesting in terms of visualizing what's going on. It's not used to delineate features with lines. So here, if I wanted to have a better feel of what's going on for my surface in the plan view, we'd turn that on. And here I didn't have to, but we're recreating the tin surface at the same time. And there we are, we have our contours. So with that, I think I'll pass it back to Erin and we'll introduce her next content.
Excellent. Let me get my screen showing again here. So this next part is really kind of expanding on the LiDAR side of things, or the DEM side of things, I should say. Now, if you noticed when Matt had that LiDAR data model up, it said it had about 2 million points. That is a great number, super flexible. And again, up to that sort of 10 million mark, we're going to be running really smoothly. As you get into larger data sets, we're going to want to start to employ some different tools in order to make sure that those models are optimized and working as efficiently as we can, obviously without compromising the quality of our data. And that's where strategic thinning starts to play a really good role. So we are strategically thinning in order to make sure that our models move fast. When we're designing, we don't have legs. There's nothing fun about clicking and waiting. And that's, the real importance here. So as you can see in the graphic up on the screen, we've got a rectangle here, our area of interest. It's got full resolution points. You can see the density of the points as we're showing them in the screenshot. Outside of that, the data has been strategically thinned. And so in this sort of section of the webinar, we're going to cover a bunch of different tools that you might use to help with those big data sets with that strategic thinning. So we do have the option with LiDAR as well as DEM data. We can thin the data at import, and we can do this against an area of interest if you know it. If you don't know it, assuming that your data is not so big that you can't import it in the first place, we can start to also employ thinning after import tools, and these ones are much more intelligent when it comes to being better at selectively thinning. So thinning at imports, just straight up skipping points. Thinning after imports, we've got better, smarter algorithms that are going to work with your data. So if you've got LiDAR data, we're going to be talking about probably the terrain modeling simplify tool. And if we've got DEM data, likely using the feature tools, simplify, smooth tool. And I'll explain a little bit about each of those. And then of course, leveraging areas of interest. Really important topic. If you don't know where it is, you also have the option to import your data thinned, figure out your area of interest, create a polygon, and then swap the model later to have full resolution data in that area. So when it comes to thinning big data, there is really a fit between the type of tool we'd recommend and the data format. So LiDAR, as Matt mentioned, it's going to be showing as individual points, although they might be grouped into features. They're not gridded or as linear as something like DEM data or contour data. So here, we highly recommend leveraging the terrain modeling simplify tool. This is going to give us an ability to really intelligently thin our LiDAR data. It can be to an area of interest, to a corridor width, or across the entire data set. When it comes to DEM data, this data is typically gridded. It's going to be contained in sort of feature rows. And here we can use the Simplify Smooth tool that's found in Feature Tools. This actually is going to use the Douglas Puker method on it and remove points that are not adding value. So if you've got Yeah, flat areas and adjacent points. So it's going to remove those points that don't add value to the model. So really, really useful and very fast running tool that you can use on DEM data. And similarly, contours, they operate kind of the same way, that those data points are contained in sort of more linear features. And there we can leverage that Douglas-Bucher method through the Simplify Smooth tool as well. So back to Matt. Let's go take a look at thinning.
All right. So before I start thinning things and manipulating things, let's flash up our example and bring in the same data set in those kind of 3 different common formats for kind of that landscape level data or remote sense data. So I'm going to come over here. I've got a different example for this one. And right off the bat, just keep in mind I'm going to be looking at the same data set for my 3 examples for each of these. I've got my contours, 186 megs, DEM, 10 megs, and then my LAZ data is pretty heavy here. So it's at 700 megs. And I'm going to start by bringing in that LAZ data just because it's the monster. It's the bigger one of the bunch. So the LAZ data is heavier because oftentimes it's including everything. So it's not just the ground points. There's all the canopy points that were hit when that surface was originally scanned. So we can, of course, bring that in. And it's going to, as it sorts through what points are tagged as being ground shots versus not, it's going to take a little while just given the size of this file. But as it plugs away, we will momentarily get a data set that imports. It'll appear as this big magenta blob to start, and then we can have a peek at what's going on there. All right, so it's drawing. Now with this, if we don't want to wait for that draw, we can hit escape on our keyboard to cancel the draw. Now with this, and as introduced before, usually I'm not that interested in where each one of these 6 million points are, kind of random where they land on the ground. So I'll just click off to the side to deselect them. And we could come over here and we could click calculate tin generate. And we can do that with this one where it's, again, a fairly small file for actually modeled ground points in it at 6 million points. It wouldn't be a problem at all here to run this without thinning. Now, if we had have brought that in and we saw that that number was, say, 100 million points, well, then I'd say, well, maybe we should use some of those thinning or other tools like, well, thinning and eliminating all the points outside of an area of interest. We could use that to help manage our file size. Now, I'll create our tin. We'll have a peek at it. So there's our surface. We can see it's a really good representation of what's going on the ground when this data was scanned. Now let's back up here. And again, we won't use the actual thinning tools. We'll just kind of look at some of the differences in format before we use the thinning tools. We're going to click Insert File. We're going to select that DEM this time. So this is a TIFF. Now the TIFF could be an image or it could be the raster data. So we're going to select that it's raster data. We'll bring this guy in. Loads much faster. We're down around 2.5 million points. And I created my contours this time too. But we can check out that 3D surface, and it's pretty similar to the last data. Now, the difference being that this, we have our points on a regular grid, so a 1 meter regular grid in this case, so it's dense enough that it does a good job of capturing our details. Now, it's not adding any details if there's gaps in that original LiDAR data. We still get a point right on top of wherever those longer triangles would be. And then we'll also introduce that modeling a surface from our contours. So here we'll click Insert File. We'll grab that contour DXF, and it could be a DXF, could be a shape, DWG, etc. A bunch of different formats that could be. We'll bring it in. And we can see we have our contours, but those contours don't necessarily mean that there's a surface yet. So we're kind of working backwards from a standard workflow here, where instead of using survey data to define our surface, we're using the contours to define our surface, which would have been a derivative of the original survey data. Now with this, it's a pretty simple process and basically the same as before. We'd come in here, we'd model our surface, these contours, we have the modeled property turned on, and there we go. So we have a couple things that are not as attractive about this surface. So let's go over here to start. Usually ridges, tops of hills, bottoms of valleys are kind of where you see the biggest kind of pain points of using contours to define your surface. So ultimately it boils down to that between your contours, you don't have surface information to define what's there. So it's stuck interpolating from your modeled points here, modeled points there. So tops of ridges, bottoms of valleys, things get flattened out. And then similarly, and here along this edge, well, we're capturing the road because we have the same contour on this side versus that side. But then our existing road gets obfuscated just because there's nothing to show us where that topography changes in the ditch. So coming back to these other formats, that's the same area. We see the road is really apparent, easy to work with. We can see what we want, and away we go. Now, aside from just these big data formats are not all equal, let's do some thinning. So right off the bat, we've already brought in, and this is the last data with our 6 million points. If I had brought that in and I decided I wanted to thin based off of a polygon, I could just draw a feature in and say I want my surface data to be included within this box. We can do that. Or a lot of the time you often have a pre-existing file that you want to use. So here I've got a polygon, and we could say, well, instead of having all this data everywhere, we could say I want to remove everything outside of that feature. So I'm going train modeling, simplify. I'm going to add in an excluded region, so that feature that we've called AOI. And then outside of that, we could tell it that, well, if we do a basic grid simplification, we could say we only want to preserve 1 point in every 10 meters. Or we could change this number. We could go up for something more sparse out there, or go down. Or if it was something that we wanted to preserve more data on steep slopes, we could use a 3D thinning. And then if we just want to basically remove everything outside of that feature, we could use our remove all points functionality. And we'll do that here. We're just going to keep everything in that specific area. We've done our thinning. We're down to 1.4 million points. We can click that generate. And voila, we've just got that surface within our area of interest now. We've got a lighter file. Now, we can also thin on import. Actually, let's just grab that feature. So, new instance of train. I'll paste that same polygon in, so it's kind of an apples to apples comparison. We can click Insert File. We'll bring in that DEM data. And, well, we can bring it in, but instead of bringing everything right off the bat, we can say, well, on import, I want to keep everything within that polygon. And here it doesn't have to be a polygon, and same with the other. We could use a corridor just based on an offset distance from a corridor. But in that area, I'm going to keep my full resolution. And outside of this, I'm going to reduce my quality. So here I'm going to say, well, instead of considering it spatially, it's just we're going to read in 1 point and then skip the next 9. We'll hit OK. We'll hit continue. We can zoom in here just to see the difference. So I've got really dense data in here and really sparse data out of it. And you can mix and match, and you can say, well, I want to try thinning on import and then realize, oh, I'm not as small of a file, and maybe we do even more. So we could thin it afterwards too. So I'm going to just remove all the points outside of that polygon. Now those thinning tools that we've introduced, they work the same whether we're using it for DEM data, LiDAR data, etc. Whatever's modeled, they behave very similarly. Now this next one, the feature simplification tool, it works well for DEM data and contour data. And I'm going to just grab one of these DEM features, and we're going to use it as a little bit of an example as we kind of look at it. So one, I'm going to make this so we can see it, even when it's not selected. I'm going to make it so we can see each point. Actually, we'll use a different symbol, and we'll make it connected. And we'll look at our profile. So that DEM data, when we first bring it in, it's not connected. If we want to see it as a line, just to make this concept make a little more sense, well, we could take this and use the feature simplify tool. So we don't want to smooth it. Smoothing is going to add more points. Simplify is going to remove points based off of a tolerance. So if I want to remove all points that are have a deviation relative to their neighbors of less than 0.1 project units, so 0.1 meters, we could run that, and this feature is going to become sparser. It's going to become sparser, but it's going to preserve the points that really drive the geometry. Now, aside from just doing this on this one feature, we can treat all of these in one go and do that 0.1, but we'll come back to that one that we've displayed as our proof of concept. So here, when we zoom out, we can see we're getting rid of a bunch of points on planar surfaces, but where there's lots of irregularity, we are doing a better job of preserving the point density. And then if we zoom into that one feature that we had selected here, we can see, and we'll also set it in profile, that yeah, we're removing the flat spots, we're preserving our points along the ridges and irregularities, and away we go. So that feature simplification, it does carry forward in well, the world of modeling our contours. And this one shouldn't be modeled. But here, it's, well, 1,000,000 points. It's not a great surface. It's 1,000,000 points. And again, if we kind of zoom in here, we can see that this is a fairly dense data set where we've got all kinds of detail around the edges. So if we wanted to make this even lighter, we could use that simplify functionality. So we're going from 1,000,000 points down to 100,000. So nice light, but we're still not going to really, we can make it lighter. We're not going to be dealing with just the fact that it's contour data and we don't have points where we'd probably like to have points to model. So that is a few kind of tricks and tools to working with big data sets. I'll pass it back to Erin.
Okay, topic number 4, and we only have 4 minutes left. Awesome. I love how we never practice our webinars before to actually know how long they're going to be. So sorry, everyone. This one's going to go a little bit longer. Topic number 4 is conventional data, and this is really, applies to say total station, RTK GPS data, and there's a few tips and tricks for importing it and working with it. First and foremost is this idea of an import specification. So when you bring your data in, we need to kind of tell the software, how do we interpret that data? Perhaps your data has, a bunch of features that are all labeled and defined, shoulder, center line, etc. How do we tell the software what to do with it? So we can set up these things called import specifications. They describe the data structure to the software, letting it know what features to join automatically, where do we create polylines, where do we put a symbol, what do the colors look like. And if you have a surveyor that is constantly giving you data in the exact same format, these import specifications are reusable and can save tremendous amounts of time between after that initial setup. So you can just import your data, apply the specification, and it's going to work. So what it's doing, kind of in a little bit more graphically explained, you've got your data, it's got point codes attached to it. The IOP file, or the import specification, basically translates all those points and point codes into meaningful groupings of feature, into meaningful line work and symbology, and it can even define things like breaklines. And as Matt mentioned, breaklines, if a feature is defined as a breakline, triangles are not going to cross over it, and you can have those defined as well on import. So working with conventional data, although very different from those big data sets and other formats we're talking about, can certainly be made easier through leveraging things like import specifications. And we'll quickly jump back to Matt and take a look at, that type of data.
All right, so previously we brought in our conventional survey data. When I brought that in, I was just bringing it in from a CSV. So pretty standard format. Doesn't have to be a CSV, could be a text file, ASCII, etc. Could be, instead of comma separated, could be tab separated, etc. Now, with that, we could come over here, pop train open, click insert file, and I'm going to grab that file. And I'm going to bring it in, and I'm going to use one of the default settings here. So I mentioned that comma separated, we can tell it what columns are X and Y and Z and point code, whether it's comma, tab, or something different. And then if we were just running with default settings, we wouldn't have it pre-formatted, so it knows that the shots that I've surveyed as CL for center line should be treated a certain way. So if we don't have codes used to define things, it's going to treat all these surveyed points kind of as being the same. So we bring it in, we see here that we've got, well, 3D points. Let's click this guy here. Oh, actually, I've got one stray point where I didn't skip my header. So we can take that and we can see our surface. Now it's not a very nice surface because those break lines don't exist. So if the surveyor had collected that data without point codes and just collected it as an XYZ format, which we will talk about here momentarily, but we could go through and we could play connect the dots and say, well, that's probably a road edge. That's probably a road edge point, and we can see the codes here, and we could hit Control J or feature properties join, and we could go through and we could play connect the dots. We can get to the same endpoint of the surface that we're working with, but it's tedious to play connect the dots and kind of define all these polylines. It's especially tedious and frustrating if they were properly coded and there's a better way. So rather than just dumping that in and treating it all as being the same, we'll use that IOP functionality. New instance of terrain, we're going to grab that CSV. So same CSV here. Instead of just using one of these two top defaults, previously I would have clicked New Format, clicked Add, gave it a name, and I would have created this guy, which has my standard survey format in it. So this concepts are the same. The only difference is that I've taken the time to define what my codes are. So that center line that I mentioned, the CL shot, is going to be brought in as a polyline. It's going to be colored red. It's going to have a triangle at each surveyed point, and it's going to be tagged as being a break line right from the get-go, so I don't have to go through and turn those break lines on and off to manipulate my surface. We should be pretty good to go pretty quick. We brought it in, we can see instead of just having a bunch of points without clear connections between them, our formatting is applied, and the points that we want treated as lines and connected as lines are connected. Now here we could go up to terrain modeling, click generate, and I'll skip my contours, but I'm getting a crossing break line. Now, if we do want to troubleshoot that, we could go and say, well, let's select our crossing break line features, so the ones that have that tag. And what a crossing break line is, if our lines are used to define where our triangle edges are, if those lines are crossing somewhere other than a vertice like this, well, the computer doesn't know where that triangle edge should be. Does it follow this line? Does it follow that line, etc.? So that is just a prompt that, well, if we want to be really explicit about things, maybe we want to control how things are connected. So we can edit things if we need to. So sometimes when we go out and collect data in the field, we maybe miscode something or put the rod slightly off where we'd like it to be, like in this case. And then we can just quickly update that, and we've got around having those crossing break line features. And then lastly, and I meant to introduce it earlier, but max section length, or max side length for our triangles. Here I've got some pretty long interpolations for our triangle edges. We can hem that down by reducing the maximum length for our triangle edges. So clipping our limit, we could also just draw a feature around that and use it as a tin boundary. But that's it. Pretty simple working with conventional survey data. Just the concept is, instead of just dealing with the problem through point density, those lines are going to matter.
Okay. Topic 5. We're going to tackle some of those other formats that are a little bit less common. As Matt mentioned, we are going to talk a little bit about XYZ files. They can represent a bunch of things, and then we'll talk a little bit about some of those other sort of standard CAD formats that you might see, DWGs, DXFs, and then finally LandXML. So XYZ. So this is a pretty generic data format, and we sometimes see it for conventional data, like Matt just showed. We also sometimes see this for larger point cloud data that represents either DEM or LiDAR or UAV data, and it's being exported that way. And so this is more just a quick courtesy message. If your XYZ data is a large point cloud, the standard formats in our software for XYZ have all the points turned on to be displayed, as you just saw with Matt when he imported it. So here, you're going to import a giant black blob. So if you know that you've got a large point cloud and it's coming in as XYZ, a courtesy note, jump into that code tab, change the display property to not being displayed, and then you can work with it afterwards, much the same you would as sort of LiDAR and DEM data once it's in. The other format that has a lot of nuances to it and a lot of variability are these CAD exchange formats, DWGs, DXFs. Their quality can vary widely. This is, obviously coming from another program that it's being created in. Sometimes you have a mixture of 2D and 3D entities in one file. And actually, if you take a look at this graphic I've got here, a perfect example of that mixed entities. You've got some points and some elements in it that have the Z value or the elevation where we can create a surface. And then you've got 2D entities that have an elevation of 0. but on import, they are being labeled as modeled, which means you go to create your tin surface and you end up with this crazy, I don't know, slice of bread looking topo surface with spikes going down to 0 elevation. So it's really important when working with DWG's DXF, trying to be aware of what's in your file. If there's an opportunity to clean that file a little bit before modeling it, maybe excluding symbols, blocks, labels, or those 0 elevation features. Yeah, and then I guess another sort of warning with it, but they tend to have much heavier performance. So they're slower than working with some of these other more native formats. So if you have the option where possible, this is probably our least favorite file type for working in RoadEng. So if you've got an opportunity for a different file type, maybe take it. And with that, I'm not going to do too much intro for LandXML. It's a pretty, interesting and unique format, an industry standard, and certainly our recommendation when importing and exporting to another software from RoadEng. LandXML is going to be our recommendation. So Nat, I'm going to send it back to you to talk a little bit about some of these alternative formats.
All right. So I guess picking up where we left off, that conventional survey data, the same file, just shown as an XML. It's there's no codes associated with it. So when we bring that in as an XYZ, we would select that it's XYZ data, and we'll hit continue, and there we are. So we've brought it in. Now, as Aaron said, if that's meant to represent conventional survey data, it may be that we want to see each one of those points. If that was the super dense LiDAR data, and here it's XYZ, but it's got a different extension name on it. We're going to bring this guy in, same concept. On our code tab here, we've got the display property set as yes. So if we were typically using this XYZ format for LiDAR data, we'd save our IOP to have that display property set to no. It's not connected. The other thing that we're doing here is we've got a max number of points per feature. And there we are. We've got our data brought in, and since we are connecting those, or they're joined but not connected, they are still grouped together. But yeah, it's just another alternative to move that data back and forth. Typically, XYZ is not a super efficient format, so it takes a little longer to load than, say, the last data, and it's not as compact as the DEM data. So let's close out of here. We'll go on to the next format in our hit list, and that's DXF or DWG. So for these ones, I'm going to treat DXF and DWG interchangeably. I'm going to click Insert. I'm going to grab one of these examples, and let's grab this guy here. So these are all DXF files, and I guess where Aaron was saying that it's one of our least favorite formats. They can be super nice and easy to work with. It's just there's a lot of flexibility in what's in there, and a lot of opportunity for it to not be organized very well. So bringing this guy in, just with our default settings, we've got points and line work. If we click the 3D view, we can see that we've got, it's all up here on the same kind of datum. We can click model and easy peasy. But the kicker is it's not always like that. So alternatively, if we pop open terrain and we bring in a file that has something that's similar to what Aaron introduced in the PowerPoint. So bringing this in using the same settings, we can come in here Now, usually when I bring in LiDAR data, my first thing to do is to look at it like that, and we can see, well, I've got 3D data, but I've also got 2D data, and I don't want it in my surface, so I would make that not modeled. But if we didn't catch that right off the bat, and we just hit train, modeling, and I won't create my contours, we've got something that looks like that, and it looks pretty scary at a glance. What's going on? But it's oftentimes fairly easy to deal with too. So we can come in here, we can hit select. Now, if we're in an instance, and I'm just going to get rid of that model so we can see the points a little bit better. But if we have something like this where the not modeled data is kind of in the same vicinity of each other, we could just click those and say, okay, this is all handy to elevation 0, select feature by range. We're going to select it by the elevation range. So we'll go -1 to 1. We've got, and of course I click to deselect that, but we'll do it again. So by range, -1 to 1. We'll include anything that's on the verge. And so we're going to just turn off that model property. If it's not 3D, we can turn off the elevation too, and then we can click generate. So we're looking much better. Kicker here though, this line work, if we knew everything was Breaklines, we could just turn Breakline property on and we'd be set. If we had different layers that we wanted to model as Breaklines, we could select those by either name or by layer and control them that way. So again, can be pretty easy, but yeah, it's less so if the data is a mess, the file's not organized well. And then the next one being, well, sometimes we get lucky. And with that, and it's going to be a kind of a segue into the LandXML format as well. But if we bring in a DXF or DWG, I'm going to leave it off for now. But if we bring this in, we zoom in and we see a bunch of features that represent the wire mesh, well, we should probably use those to define our surface. Now we could, kind of after the fact, select all our triangles, make them break lines, make everything else not modeled, or we could have brought this in and had this turned on. So here, those triangle faces are not brought in as features. Instead, they're brought in defining the surface on import. So we don't have to go up here and click generate pin. And this is nice because it's going to preserve the triangle edges exactly as they were in the other software. So if you want a carbon copy of one versus the other, it's yeah, really nice to avoid any ambiguity, because there can be a little bit of ambiguity, especially with conventional survey data. So our break lines control where the triangle edges are that we specifically want to control. But if we had something like this, where that point to that point was a model or happened to be a triangle edge, well, and we wanted to preserve that that was a triangle edge across different and here I select feature. I included everything in there. Select by range. So I'm going to have remodeled it with everything that I had manipulated, and let's turn that guy off. So model off. Yep. So if we're using that to define our triangle edges and we want that exactly as is, so basically every one of those triangle edges moved over to the other platform, well, saving as a LandXML is nice for interoperability or importing as a LandXML, or triangle edges. Now, that was triangle face is defined in a DXF, and I got tripped up with my words there, but LandXML, that's one of the big benefits of LandXML is the triangle edges are going to be defined in it. So here I'm going to bring in that conventional survey data as an XML. Here we can choose if there's multiple surfaces in our file, which one we bring in. We can hit OK, and voila, we have that surface as a carbon copy with everything defined as it was when that surface was created. One thing that I will mention, I guess, for LandXML data, when we bring this in, those points are displayed. So typically it's used to not so much be used with the big data sets. So conventional survey data or design surfaces, oftentimes we'll want to see those points, but if those points are not of much value to us, we can turn that off. And yeah, we don't have to deal with the clutter. Now that being said as well, LandXML is a fairly heavy surface, so I wouldn't use it as my default for, say, something like a big data set, landscape level surface. Yeah, DEM is pretty concise, and there's not a lot of variability in where those triangles are going to be, since it's going to be limited by your grid spacing. So with that, we've got our alternative formats covered, and I'll pass it back to Aaron.
Okay, guys, last topic. Here, we're just going to briefly touch on the concept of quality and resolution. And I think it's important, as we've gone through all these different types of data and their formats, to remind everyone that not all tin surfaces are the same resolution. And we've got sort of 3 examples here spanning from sort of some SRTM data over down to LiDAR. And really, the density and the sparsity of the points in your data set is going to control how large the triangles are and really, what quality that surface is when it comes to making your engineering decisions. So a couple caveats, or I should say notes. So RoadEng does not discriminate against any tin surface. You can literally put in SRTM data and it's going to be happy to work with it. It's an engineering decision. If you are okay with the quality of surface you brought in, if it's prelim design, maybe that you can get away with that. And the impact of this difference in surface really can be felt through volume differences. So if you, had a, say, an example road design and you swapped out the surface from this sort of SRTM low resolution data to some higher resolution data, you're going to see differences in terms of the volumes, because now we're seeing more of the ground, we're understanding it a little bit more. And we just wanted to put this one in as a reminder to everyone as you're, working with and data and creating surfaces, just being aware of, that not all tin surfaces are the same. I don't know, Matt, we were hoping in our, haste of preparing this webinar to actually have an example of this one for you guys. Ran a little bit short of time, but I don't know, Matt, do you have anything else to add on this topic?
Not much. Yeah, it's not all survey data or surface information is created equal. And as Aaron said, the density of the data is important. Aside from just the density, though, too, just because you have lots of points or lots of lines doesn't mean that it's good data as well. So your accuracy is going to play into it. Yeah, so conventional survey data is obviously pretty dependent on where the surveyor puts the rod and decides to measure a point. In the remote sense space, and it's something that we occasionally see, and something folks should avoid. Just because you have a DEM with a 1 meter point spacing doesn't mean it's good data, especially if that DEM was generated from a 30 meter DEM before it. So upsampling doesn't improve the quality. And then the original accuracy of the surface too. So SRTM is kind of a global data set, typically 30 meter-ish point spacing, but it's satellite derived. There's a lot of variability in the elevation. So aside from just things getting smoothed out with that sparser point spacing, the vertical accuracy is going to be off a bit, sometimes quite a bit. So a 30-meter DEM that was down sampled from LiDAR data is going to be better than a 30-meter DEM from SRTM or other really coarse original data sets. Yeah, that's it for me.
Awesome. And guys, we're 21 minutes over. I think this might be a record for most overtime webinar we've done, Matt. Oh, terrible. Okay, with that, let's tackle 2 questions just to make it even longer. So Matt, I'm going to send it back to you here and make you the presenter again. First question, is it possible to combine some of these data formats? In this particular, this person was asking if they could combine LiDAR with some conventional survey data.
Yeah. So yes, you totally can. And it's actually pretty forgiving. Now this one is from the LandXML that I just created. Oh, let's go back. I guess we're this far over already. Why? So I've got my conventional survey data, and is this the big one? Okay, we're going to switch which one I use here. We've got this conventional survey data, and I of course didn't save my surface, but it's on the same project footprint, just a smaller subset of it. So we're going to grab that guy, conventional. We're going to bring in the, bring it in with the IOP that we'd like. We're going to model our surface. And I will just quickly tweak those crossing break lines. Where is that other one? There we are. All right, so if we were combining our data sets, and I guess I should have prefaced this. One, we could totally just dump this right into LiDAR data and we'd have lines with the same information. Now, oftentimes that's not desirable. It gets a little funky, particularly in things like our ditches. The LiDAR data may have points here that are just poorly classified points. It might be a bush got coded as ground instead. So usually if we're combining our LiDAR data sets and we have something that's a full surface survey, we want to use that with our conventional LiDAR surface, we'd take this. We're going to be a little bit more pragmatic about trimming our edges out here. So we could say, well, there's our tin boundary as is. So this blue line going around here, and I'm not going to do as good of a job as I probably should for the sake of time. But we keep that as tight as we are comfortable with the surface data. Then we'd say, well, that's a tin boundary feature. So rather than having big interpolations across there, we could hem this in. So we'd say it's a tin boundary. We'll model it as a break line. And that's our, we'll call it TS. So total station data. Now the LiDAR data, and I think I do have that one saved. Let's see if I just closed it or if I hit save. Open. There, I do have it. So my LiDAR data, or my LiDAR terrain file, I want to replace where these two overlap. So from my bigger surface, typically the LiDAR surface, we'd come up here, we'd go terrain modeling, we'd click merge, we'd choose this other one. So, and there it is. We'd hit OK. And what it does is it's going to basically clip the LiDAR data within this, put a boundary around the edge, and then set that other data set in here. We don't necessarily need the boundaries if we didn't want to include them, but I will for now, just for showing it. So we can see all the LiDAR data, that new vector data that we brought in. There was a warning there briefly that said our surface is out of date. So there's no surface. We'd come in here, we'd remodel that. And we're set. Now, on this edge where I did take some time to actually stitch things together, it looks good. But over here where we have these really long interpolations, well, we can see those long interpolations don't marry well with the surface. So here where I didn't change it, I should have brought that in closer to my surveyed area. Or perhaps it would have looked even better if we didn't have those boundary features created. So, and of course, just kind of, yeah, combining data, super easy, especially when everything lines up. But occasionally there's biases as well. So if it was that my total station data happened to be on a different datum or something, we wanted to shift it up and down, and we'd kind of do that check and moving things around before we actually hit the merge button. So yeah, it's pretty straightforward, but a little bit of extra work if things don't match up well. Hopefully that answers the question.
Awesome. Thanks, Matt. That was a very long answer and certainly more thorough than I was anticipating. I guess a benefit of having a similar data, or I should say the same sort of area being modeled in a few different data formats, you could actually execute it. With that, guys, we are now pretty much half an hour over time. There are a couple complicated questions left in the chat. We're going to tackle those individually with those askers. And with that, thank you for hanging out with us till the end. I hope that you found some of today's tips, tools, and different demonstrations useful. Apply the ones you need to your different data format. And we look forward to seeing you guys all at another webinar coming soon. Thanks, Matt. Yeah, a lot of heavy lifting on your side today. So well done.
Cheers, everyone.